Can everybody hear me okay? Um,
Yes.
Great, super. So thanks very much to the organizers for having me. And it's nice to follow on this talk by Tanima. I'm going to also focus, which is about supermassive black holes over cosmic time, but I as well am particularly interested in the effects of obscuration. And so I'm going to give kind of a broad overview of some of the work that the field and people in my group in particular are doing, studying the hidden and elusive growth of black holes over cosmic time. So first off, just as a general picture, how do we find elusive black holes? Well, the first question is, how do we identify AGN at all? It's instructive to take a SED of a galaxy, which is, basically host galaxy light, dust from star formation, hot gas, and binaries. And then if you add in a growing black hole to it, you can see that an unobscured AGN dominates across almost the whole electromagnetic spectrum. So there's lots of different signatures that we can identify. And so that's the subject of whole conferences. But you can see some of the highest contrast is in the X-rays. So as Tonima pointed out, that's often the approach that people have used to try to get a complete census of black hole growth is using X-ray observations. And I just want to highlight a little bit about this. So Tonima already discussed how you use X-ray observations to trace the growth of black holes, basically just assuming some radiative efficiency to get the total density of black holes over cosmic time. And if we do this, one of the interesting things that you find is that the growth of black holes is basically approximately follows that of star formation, with a peak around between redshift 1 and 2 and dropping off by more than an order of magnitude to lower redshift. And so to actually do this, to trace this whole thing out of how black holes grow with their host galaxies, the most common or perhaps most powerful tool people have used have been X-ray surveys. And by the way, I won't state them, but I'll highlight in blue here some of the other presentations at this meeting that are relevant to a lot of these topics. And I would encourage everybody to go look at all the talks, as Patricia said, even the ones that are not being streamed live. So X-ray surveys, how do we do X-ray surveys? Well, you can take wide field areas. This should say published. This is the wide area Chandra survey in the X-Booties field. And so we can zoom in and get deeper and deeper over smaller and smaller areas and trace out a large range in luminosity and redshift, as Tanima discussed. And so you could, again, write a whole conference about the topics I put in this one slide, but just for the key results, not necessarily talking about obscuration, key results from AGN surveys are that AGN are found in all types of galaxies, both in terms of morphology and star formation. But on average, black hole growth broadly follows star formation and or stellar mass in galaxies. But there are some interesting dependencies on, for example, morphology or environment. Like very compact galaxies seem to have more rapid black hole growth in general. And so this is the sort of general picture. You get downsizing where big objects form first. That happens in galaxies, and it also happens in black holes. But an important distinction, an important thing to keep in mind that hasn't been mentioned much so far at this conference is that instantaneously AGN can have a very broad range in accretion rates. They're not light bulbs. They flicker over a wide dynamic range. And so when you're looking at one particular galaxy, those timescales can be pretty short. So we have to think about this as a statistical problem, and understanding the exact lifetimes of AGN and how we map the long-term growth of black holes to the instantaneous things we observe is something that's an important factor that we have to keep in mind. So that's the big picture. And that's where, there's obviously lots of details. But a really important thing that we've learned, I'd say, in particular over the last 15 years or so, trying to get my focus working here, is that most AGN are actually hidden by gas and dust. And so this is 3C273, the first quasar discovered. You can see the obvious optical emission from this source. But if you look at a high redshift AGN of a character of still a pretty high luminosity, they often just look like galaxies. Most of their light has been obscured, and there's been a lot of work by a number of people looking at this. And so how do we identify these obscured sources? Well, if you take obscuration and put it in front of the nucleus of an AGN, what it does typically is it will obscure the optical and ultraviolet and the soft X-rays, leaving the hard X-rays and the infrared. And so one of the most powerful methods we can use for identifying these obscured objects is using, in particular, infrared techniques that can penetrate this gas and dust, and then the X-rays to get some handle on the obscuration. So people have been doing this, and oftentimes people often use the details of the X-ray spectrum. And this is Tanima showed some nice figures showing the effects of obscuration on the X-ray spectrum. So there's been a lot of work on this, and people look both in the local universe and across cosmic time. And one of the main things that people have found is there is a dependence on luminosity, for example, in obscuration. But even at the highest luminosities, most of the AGN are obscured. And that obscuration actually extends to quite high column densities, well into the Compton-Thick regime, as Tanima pointed out. And one of the important things to keep in mind with that is that the observed set of objects that you find don't represent the whole NH distribution, especially if you're using an X-ray selected sample, because the X-rays will be suppressed, and so you have to correct for the flux limits of your survey. And this is something that Claudio Ricci did in his paper from a few years ago, finding indeed a large population of Compton-Thick AGN. So that's the sort of general landscape. What are the interesting questions that we're looking at right now? Well, here's three, and I'll go through each of these in a few minutes each. So the first is, how heavily buried and widespread are these obscured AGN? Second is, what's the actual physical nature of the obscuring material? And then finally, how did the first black holes form at the dawn of the universe when there was a lot of gas around and there probably was a lot of obscuration? So this first question, how heavily buried and widespread are these obscured AGN? Really, I think we're most interested in these Compton-Thick sources out here, the ones that are kind of hard to find. And so, you know, how many of these sources are there really, and how well are we doing this correction? Well, Tanima just showed you, and this is another version of a plot that she showed. She just showed you that the Compton-Thick fraction, when you model the X-ray background, is quite high, and perhaps higher than you would get using a strictly X-ray selected sample. And so this would indicate that indeed there's a large number of these Compton-Thick objects out there, many of which will be so suppressed in the X-rays that you won't actually be able to see them in an X-ray survey. So how do we find these things then? Well, what you can do, as I mentioned before, is use both the X-ray and the infrared luminosities. So since the X-rays are being suppressed, but the infrared not so much, if you can find the signatures of a growing black hole in the infrared and then measure the ratio of the X-rays to the infrared, that gives you some handle on how heavily obscured they are. And there's complications here. The obscuration can affect the infrared SED as well. And so you won't pick up everything, but this is a interesting approach for trying to find some of these very heavily buried sources. So we did this in our group, and I'm going to highlight a few papers now by members of our research group here at Dartmouth. This is one by Vivian Yan from 2019, where she did new star observations of a set of powerful AGN that we identified in the infrared with WISE. And of the four that we observed, only one of them was detected, and this is only very weakly. This is a new star image. And so if you go to plot this on a figure that shows the infrared luminosity on the x-axis and the X-ray luminosity on the y-axis, an unobscured source would typically have a relationship that looks up here. And she found very heavily suppressed X-ray emission by up to as much as 2 orders of magnitude, suggesting that these things have a really, really high obscuration, even above 10 to the 25 per square centimeter. And so if you put that together and try to make some assumptions about the infrared population and turn that into a column density distribution, that gets you start to find a lot of these objects with extreme obscuration, even more than 10 to the 25. So this is pointing us in the direction of things that maybe we would not find in X-ray surveys. So our group has continued this by now saying, okay, let's not just target a small handful of them. What if we look at the whole sky? So there's a nice WISE AGN catalog that was produced by Roberto Assef a few years ago, as one of a couple that did this. I think Nathan Seacrest had one as well. And so we took Roberto's catalog and found all of the sources across the whole sky that had both some kind of redshift information and also were located inside of an X-ray field with Chandra or XMM or NuStar. So this is work by my student Chris Carroll. And this shows, this plot's got a lot here, but just the key axis here is this ratio, which is how luminous the objects that we find are in X-rays compared to what you would expect if they were unobscured. So an unobscured source would be up here. And he finds most sources are suppressed in X-rays, and a lot of them, even bona fide wise AGN, have only upper limits in our X-ray observations, which corresponds to some fairly large NH for a lot of these. And so he did a distribution of column densities that came out of this particular survey, did an estimate, and found that there are a lot of things that are pushing up against this 10 to the 25 or higher column density. And one of the really most interesting things that came out of this is because these were all in X-ray fields, at least for the Chandra sources, we were able to stack the X-rays. And we found that the X-ray undetected sources, the X-ray detected ones, the blue stars here, have really bright X-ray detections. But even the X-ray undetected ones have clear X-ray emission that is consistent with there being underlying AGN there. So these things that we don't have direct X-ray evidence that there's an AGN there, but they look like AGN in the infrared. They seem to be heavily suppressed. They probably are these very obscured AGN. And so Chris is right now, this paper actually was just accepted. It's going to be on the archive tomorrow. So have a look in the morning for that. He's currently working to do a more sophisticated estimate of the NH distribution. Okay, so the takeaway, there's obviously a lot of other people working on this topic, but the takeaway is that obscured AGN can be extremely heavily buried. And in fact, I think we're going to have another talk by Lambrides later in this session that will show some really interesting work in this topic in the Chandra Deep Field South. But the main takeaway is that they can be extremely heavily buried and make up the majority of growing black holes, and they may be missed in many studies. And I just want to highlight here again the point that Tanima raised, which is this has an impact on the average radiative efficiency of AGN, because if there are these missing objects, you add them in, that then affects the overall radiative efficiency. Okay, so we have these heavily buried sources there, but one of the still outstanding questions is what's the physical nature of the obscuring material? Like, where is this coming from? You know, you have this standard unified AGN torus model that we all know and love, but that's obviously not the whole story. We think that, you know, the amount of obscuration can depend somewhat on the scale that we're seeing, but we don't know, for especially these distant sources, exactly what the source of the obscuration is. And so just to show a couple results from simulations, we know for sure that there's a dusty torusy thing that's probably clumpy and dynamic and has polar structures and all kinds of stuff. But some of the obscuration is clearly coming from something on sort of parsec scales. And that's shown by, Conrad Tristram showed those wonderful observations of nearby AGN earlier in the meeting, and there's lots of evidence for this. However, we also think there can be obscuration in the scale of the host galaxy. And one obvious way to do that is through a galaxy merger. This is a nice simulation by Laura Blecka and collaborators that shows that when two galaxies merge together, you can get a very large column density at the moment when they coalesce and the accretion rate is the highest. And so we may expect, and you can also have objects that are just edge on, that you're just looking through material in the host galaxy. And so some of the obscuration happens on these larger scales. And so one interesting question is to ask, okay, well, can we tell those things apart? And one way to do that is to look at galaxy scales and larger scales for the of the obscured and unobscured systems. And so if you have a torus, it's just orientation. In the simplest picture, there really should be no difference in the host galaxies and large scale structures. But if you have some sort of galaxy scale or evolutionary process, then it's possible that hosts of obscured sources will look different than unobscured ones. And so people have looked at this in a number of different ways. One is looking at mergers. And there's still a lot of debate about this, but I think some of the evidence is pretty compelling that dust reddened or heavily obscured AGN are more likely to be found in mergers, or the flip side is that mergers are more likely to host heavily obscured AGN. So that's giving us some evidence for that picture that I showed from those simulations. Also, if you look at star formation, if you look at the most powerful objects, this is work by my former graduate student Chen-Ting Chen for his thesis, the more powerful star-forming quasars have a higher obscuration fraction, suggesting that some of that gas that's associated with the star formation and dust is actually obscuring the central engine. Lastly, what we can do is look at the large-scale structures of these systems by measuring their clustering and by cosmic microwave background lensing. And thanks for the time update. And so you can either measure how things are clustered in space, or you can measure the integrated lensing signal along the line of sight. This is something our group has been really actively involved in, and I'm not going to go through all the details of this, but just to highlight a nice paper by Mike DiPompeo from a few years ago, where he kind of put this all together, and ultimately obscured quasars are more strongly clustered than their unobscured counterparts. And I think we've established that now pretty clearly. And my student Kelly Wayland had a nice paper showing that secular processes, like just a dependence on Eddington ratio or host galaxy mass, are actually not enough to produce the clustering differences that we see. So this implies that, in fact, there are evolutionary processes like the merger simulation that I showed that are responsible for some of the obscuration in these systems. So the takeaway is that the nuclear component is important, but some of it must come on material on larger scales, and that must be associated with evolution, or could at least be associated with evolution. So finally, just to highlight really quickly, obscured AGN at the dawn of the universe. So we saw some nice talks earlier about the formation of the first black holes, and that's an environment where there's a lot of gas and dust around. So we may the techniques that we use to find black holes must be impervious to that kind of obscuration. But the first thing we can do before even there is as we heard in particular from several people, including a nice invited talk by Amy Rines, is to look at dwarf galaxies in the nearby universe and look at AGN. And I'd like to highlight one particular result by an undergraduate in my group, Jack Parker, who's finishing up this paper, that we found a X-ray AGN identified with X-rays in the nearby dwarf galaxy Markarian 462 that clearly has an AGN emission in the X-rays, but it's much weaker than the infrared that you determine from spectral fitting, and also what you get from looking at its optical line luminosities. And so this is probably a Compton-thick AGN in a nearby dwarf galaxy. And if there are a lot of other ones of those around that will be harder to find than have been used using typical techniques, this could affect, for example, the inferred black hole occupation fraction. So that's one thing. But as Jenny pointed out, that occupation fraction has some degeneracies in terms of determining what the actual seed mechanisms are. So what you would really like to do, keep going here, is observe this directly. And so I would be remiss if I didn't mention LISA. Obviously, LISA is impervious to obscuration by gas and dust. So mergers will be telling us a lot of really interesting things. But ultimately, we would really like to probe these objects via accretion. And deep X-ray surveys in the future are going to give us really interesting results for that. So this is from a white paper led by Francesca Chavano and Nico Capelluti and myself from last year. And this just shows the sort of parameter space that was being covered by X-ray surveys. And so Athena will start to get to very high redshift, but still fairly luminous sources to find those most massive black holes. If we can then build LINX, as many of you are aware, is the sensitive high-resolution X-ray observatory that's been put forth to the decadal survey. Then we can probe down to low luminosities, which correspond to low Eddington limits, small black hole masses. And if we put this all together, we can begin to find, 10 to the 5, even 10 to the 4-ish solar mass black holes accreting at around redshift 10. And so this is important for identifying this the accretion growth of these very first black holes. And also it's important to point out that at these redshifts, even in soft X-rays, you're probing very high energy X-rays that are very penetrating. So I think a lot of this growth will be obscured, but the X-rays can help with that. And so just the takeaway from this last point is that heavily obscured AGN and dwarf galaxies may be an important population of these seed black holes, and using Athena, LINX, LISA, and also JWST, which is critical for identifying the host galaxy of these or identifying infrared signatures, we can probe the growth of seed black holes even if they are heavily obscured. And so with that, I will leave it here and say thank you very much. I look forward. I'll pop over on a Slido and look forward to your questions. Thank you.